So today we're actually going to talk about propositional logic, which is the simple part of first-order logic, where you only have propositional letters standing for atomic sentences. And you combine them with propositional connectives like negation, conjunction, disjunction, implication, and so on. And you use parentheses. So again, I'm assuming you have seen formulas like these. So maybe I write P and Q implies not R, or you see this kind of formulas. There are infinitely many of them. You can make them, they're all finite, each of them, but you can make them as longer and longer. So there are clearly infinitely many formulas, and you should recognize these. But my question now is, how can we give a precise definition of this infinite set? We're going to need that because we're going to say things about all the formulas. We're going to say that all the formulas have some property, but that's an infinite claim, a claim about infinitely many things. So we need to be able to prove such a claim. And that requires a precise definition. Well, here's what such a definition could look like. It's an inductive definition, and you will meet many inductive definitions in this course. So you see, it has a basic, the first part says that propositional letters are formulas. So we're defining the concept or the notion of a formula. The second clause says that if you have a formula and put a negation sign in front of it, you get another formula. The third clause says that if you have two formulas, phi and psi, and you write a conjunction sign between them and then parentheses around the whole thing, you get a new formula, phi and psi. And similarly for phi or phi implies psi, or phi if and only if psi, these are all formulas. These are formulas. And the fourth clause says that nothing else is a formula. This fourth clause is something we will not mention. It's taken for granted. So if you have a definition like clauses 1, 2, 3, then that is an inductive definition of the whole infinite set of formulas. Because you can see that every formula that is well formed, that is correct, is formed by applying these rules a finite number of times. You always start from propositional letters and then you apply negation or conjunction or disjunction, etc. There is more compact and nicer way to write this inductive definition, which is used in computer science, for example, very often, but also in logic. So here you see the same definition, exactly the same definition, but written in a more compact form. So it starts with P, and then negation, conjunction, disjunction, etc. Those are the inductive clauses. So, and what is P? Well, P belongs to a set of propositional letters. We're thinking we have a list of propositional letters, P0, P1, P2, but we don't use all of them. We might take just 1 or 2 or 3 propositional letters and call the set of that a vocabulary, and then look at all the L formulas, the formulas that are that can be written when you start from these, let's say, 3 propositional letters and apply the rules. Okay, so well, I haven't seen any questions or raised hands. I'm taking that to mean that everybody is happy and that there are no problems and that what I'm saying is completely clear. But if not, again, raise your hands. Okay, now let's say something about parentheses. Suppose I write something like this. Whoops. P and Q or R. Well, that is not well formed. And in fact, it's ambiguous because it could mean P and Q or R, or it could mean P and Q or R. So it's, if I write without parentheses, it's syntactically and semantically ambiguous because these 2 formulas with the parentheses mean different things. The first one says that P and Q, either P and Q holds or R holds, and the first one says that P holds and either Q or R holds. Those are different claims. Now, are these formulas according to the definition we just saw? No, because if you strictly follow that definition, you should have written like this. You should have put the outer parenthesis there too. Because every time you apply a connective, except negation, but all the binary connectives, you have to put parentheses around it. That's because when you keep going and make it a bigger formula, then you need the parentheses. But of course, you don't really need the outer, the last parentheses. So one convention that we'll use all the time is that we'll drop those. So we'll actually write the formulas as in the middle column here. So that's one kind of convention. Here's another kind of convention. Suppose I write like this. P and Q and R. That again is not strictly speaking well formed. And again, you could put parentheses in 2 ways. You could write P and Q and R, or you could write P and Q and R. So writing without parentheses is syntactically ambiguous, but this time it's not semantically ambiguous because these 2 formulas have exactly the same truth conditions, as you probably know and as we'll see. That means it doesn't really matter where the parentheses are put, so we can actually skip them, and that's another convention. We will write P and Q and R, and similarly for disjunction, P and Q and R means that all of 3 of them are true. P or Q or R means that at least one of them is true. So that's another convention. Finally, we will write things like this. Again, this is ambiguous, but this time we will actually choose one of the readings as the default one, namely this one. So that means that conjunction in this case binds stronger than implication. It's convenient sometimes to leave out those parentheses around the conjunction and just write, excuse me, as we have done to the left here. It's actually a convention that you are familiar with. Think about your addition and multiplication. If I write x times y plus z, everybody knows what I mean by that, and everybody knows that I don't mean this, but what I mean is this. So it's the same thing here, that multiplication binds stronger than addition. And we have a similar situation in logic, in propositional logic. Okay, that was just some conventions. Let's get back to inductive definitions. The point of them, as I already said, is to prove true claims about an infinite set of objects, which can be formulas or numbers or proofs or derivations or anything that has been inductively defined. So how do you prove that all formulas, every one of the infinite number of formulas, has a certain property P? That's, as I said, it's a claim about an infinite set, so you cannot just prove that by enumerating the formulas and prove it one by one, because that would take an infinite amount of time. Instead, you do the following. You prove that the sentence letters or the atomic formulas have the property P. That's the base step. Then you prove that if a formula has the property, then the negation also has the property. And if two formulas, phi and psi, have the property, then their conjunction also has the property. And similarly for the other connectives. So these are maybe 5 facts that you need to prove. Not an infinite number of facts, just 5 facts. But when you have done that, it follows that every formula has property P. So that's something we will see many, many examples of in this course, and I hope you'll see one later today in this class. But before we get there, we go on to some other things. Okay. That was the syntax of propositional logic, what the formulas look like. Now we come to the semantics, what they mean. And meaning in logic is the same as truth conditions. So we need to explain exactly under what circumstances formulas in propositional logic are true or false. And as you know, the standard way of doing that is by truth tables for the connectives. So I'm using 1 here as the truth value true and 0 as the truth value false. So when you have that, you can write some familiar truth tables, like let's write a table for negation. So here is phi, here is not phi. There are 2 possibilities for phi. It's true or false, and then the negation turns that around. So that's what you can say about negation. Let's give another example. Let's take implication. So now there are 4 possibilities. Sorry. Four combinations of truth values of the arguments. And as you hopefully remember, this is the truth value of the implication. It's only false when the antecedent phi is true and the consequent psi is false. Under all other circumstances, it's true. And similarly for, you know, the tables for conjunction and disjunction and so on. So these tables actually tell you what the connectives mean. They tell you everything there is to know in logic about what the connectives, in propositional logic about what the connectives mean. But I said we wanted to say precisely under which circumstances a formula of propositional logic is true. Well, that of course depends on the atomic or the sentence letters. So we have to assign a truth value to them, and such an assignment is called an interpretation, or in the case of propositional logic, a valuation. It's a map. It maps propositional letters to truth values. So more precisely, if L is a vocabulary, remember that okay, excellent. Now I have a question, and let me just read the question. Yes, the question is about the third line in the truth table for implication. So basically this line here. And the question is, why is this why does this get the value 1 and not 0? Well, you could say that it's by stipulation, but this is simply the definition of what this arrow means. It means, it's called material implication. It's not the same as the word implies in English or Chinese, or follows from. That's another kind of implication.